Okay, so the number 1 in the complex plane is the ordered pair 1, 0. The principal argument of the number 1 is 0, which is a value between negative pi and pi. And the modulus of the number 1 is the number 1. So the formula c sub k, which again is the nth root of the modulus of z times the ordered pair cosine of theta plus 2 pi k, all of which is divided by n, sine of theta plus 2 pi k, all of which is divided by n, can be simplified greatly in the case of roots of unity, the nth roots of unity. The modulus is always 1, the principal argument is 0, and so in the case of the nth roots of unity, the formula c sub k is the ordered pair cosine of 2 pi k divided by n, sine of 2 pi k divided by n. So in the case n equals 2, that is the square roots of unity, we now compute the elements in that set. C sub 0 is the ordered pair cosine of 2 pi times 0 divided by 2, sine of 2 pi times 0 divided by 2. This is the ordered pair cosine 0 sine 0, which is the ordered pair 1, 0, which is the real number 1. The second square root, c sub 1, is the ordered pair cosine of 2 pi times 1 divided by 2, sine of 2 pi times 1 divided by 2, which is the ordered pair cosine pi sine pi, which is the ordered pair negative 1, 0, which is the real number negative 1. And so the set of the square roots of unity consists of negative 1 and 1. No surprise here, but let's look at the geometry for a minute. The nth roots of unity will always occur on a unit circle in the complex plane. One of the nth roots of unity will always be the real number 1. Now, in general, the nth roots of unity will occur 2 pi divided by n radians apart. So in our case, we have 2 pi divided by 2, or pi radians apart, which is 180 degrees. And so the second square root of 1 is the number negative 1, once again 180 degrees from the number 1. Okay, so now let's look at the cubed roots. So the case n equals 3. There will be 3 cube roots of unity. C sub 0 is the ordered pair cosine 2 pi divided by 3. 2 pi times 0 divided by 3, and sine of 2 pi times 0 divided by 3, which is the ordered pair cosine of 0 sine of 0, which is the ordered pair 1, 0, which is the real number 1. C sub 1 is the ordered pair cosine 2 pi times 1, that is 2 pi, divided by 3, sine 2 pi divided by 3. Now 2 pi divided by 3 occurs in the second quadrant, and in the second quadrant the cosine function is negative while the sine function is positive. This is an angle based on pi over 3 radians, that is 60 degrees, and so we have cosine of 2 pi divided by 3 is negative 1/2. Sine of 2 pi divided by 3 is the square root of 3 over 2. We can write this as a sum. This is negative 1/2 plus I times the square root of 3 over 2. Okay, let's compute the last cubed root of the number 1. C sub 2 is the ordered pair Cosine of 2 pi times 2, that is 4 pi, divided by 3. Sine of 4 pi divided by 3. 4 pi divided by 3 occurs in the third quadrant. And in the third quadrant, both the sine and cosine functions are negative. And so this is the ordered pair, negative 1/2, negative square root of 3 over 2, or we can write this as the sum, negative 1/2 minus I times the square root of 3 over 2. And so the three cubed roots of unity are the numbers 1, negative 1/2 plus I times the square root of 3 over 2, and negative 1/2 minus I times the square root of 3 over 2. Once again, let's look at the geometry. The nth roots of unity will always occur on the unit circle, one of which is always the real number 1. All the others will occur at 2 pi divided by 3 radians apart, or 120 degrees apart. So 120 degrees from the number 1. We have the number negative 1/2 plus I times the square root of 3 over 2. And 120 degrees from this, we have the number negative 1/2 minus I times the square root of 3 over 2. So knowing the geometry, we can very quickly determine the fourth roots of unity. Once again, the nth roots of unity always occur on the unit circle, one of which is always the real number 1. Each will occur at 2 pi divided by 4, or pi over 2 radians apart, which is 90 degrees. 90 degrees from the number 1 gives us the number I. "90 degrees from this, we have the number negative 1. And then 90 degrees from this, we have the number negative I. And so the set of fourth roots of unity is the set containing the numbers negative 1, 1, I, and negative I. All right? Okay, so next I want to state Euler's formula. And this is a formula for imaginary exponents for the number e. E to the power of I times theta is the ordered pair cosine theta sine theta, or as a sum is the sum cosine theta plus I times sine theta. Now, we're not going to demonstrate it here, but for a complex number z, which is an ordered pair xy, or a sum x plus I times y, the complex exponents behave exactly the way that real exponents do. For instance, e to the power of z is e to the power of x plus I times y, which is e to the power of x times e to the power of I times y, which gives us e to the power of x times the ordered pair cosine y sine y. But for our purposes, Euler's formula will allow us to express complex numbers in what is known as the exponential form. In the trigonometric form, we have that z is the modulus of z times the ordered pair cosine theta sine theta. And as we can now express this ordered pair in terms of the an imaginary exponent of e, we have this is now the modulus of z times e to the power of I times theta. And once again, we refer to this as the exponential form of a complex number. All right? All right, so let the set U be the set of all complex numbers such that the modulus is 1. Then the set U is the unit circle in the complex plane centered at the origin. Now for every number, complex number on the unit circle, we can write that complex number in exponential form. Now because the modulus is always 1 for the complex numbers in the unit circle, we can simplify this as e to I times theta. Now I'm going to introduce a new notation using the symbol for the reals with a subscript of 2 pi. This is used to denote the half open interval from 0 inclusive to 2 pi. Then for every complex number on the unit circle, each complex number on the unit circle is associated with a real number, theta, in this half open interval. So, for every 2 complex numbers on the unit circle, their product can be expressed as the product of 2 exponents, e to the I theta 1 times e to the I theta 2, and this is e to the I times the quantity, or the sum, theta 1 plus theta 2. So notice that multiplication of the complex numbers on the unit circle is associated with addition of their arguments. So if we require that this sum be restricted to the interval from 0 inclusive to 2 pi, then we can define a new operation. So once again, let r sub 2 pi be the half open interval from 0 to 2 pi. Addition modulo 2 pi is the function which we'll call phi, mapping ordered pairs of numbers in the half open interval back into itself, defined by theta 1 plus, with a subscript 2 pi, theta 2, is the number theta, capital Theta, where this number theta, capital Theta, is an element in the half open interval that is coterminal with the normal sum of the arguments, theta 1 plus theta 2. So notice the set of nth roots of unity is a finite subset of the set of complex numbers on the unit circle. Now let's review addition modulo n real quick. Again, the set of integers mod n is the set of integers from 0 to n minus 1. Recall that addition modulo n is the function which once again we'll call phi, mapping ordered pairs of integers modulo n back into itself, defined by a plus b mod n is the number r, where r is the remainder when the normal sum a plus b is divided by the integer n. Now, let zeta to the power of k be the number e to the power of I times 2 pi times k, all of which is divided by n. Then the set of nth roots of unity can be expressed as the set containing these numbers zeta to the power of k, where k is an integer mod n. So notice that for every two elements, zeta to the power k1, zeta to the power k2, in this set, that the product, zeta to the power of k1 times zeta to the power of k2, is the element zeta to the power of k1 plus k2. We're going to demonstrate that this element is once again in the set of nth roots of unity. So there are three cases we need to consider. Right, case 1. Suppose that the sum k1 plus k2 is equal to n. Then zeta to the power of k1 plus k2 is equal to zeta to the power of n, which is e to the power of I times 2 pi times n divided by n, so just e to the power of I 2 pi. This is the ordered pair, cosine 2 pi sine 2 pi, which is the ordered pair 1, 0, which is the real number 1, which we can also express as zeta to the power of 0. And so zeta to the power of k1 plus k2 is equal to zeta to the power of 0, which is an element in the set u sub n. So case 2, suppose that the sum k1 plus k2 is less than n. Then the sum k1 plus k2 must be less than or equal to n minus 1, since n minus 1 is the largest integer smaller than n. Now, since the sum k1 plus k2 is the sum of two integers ranging from 0 to n minus 1, their sum must be at least twice the smallest, which is 0. And so we have that k1 plus k2 is greater than or equal to 0 and less than or equal to n minus 1. And so zeta to the power of k1 plus k2 is an element in the set u sub n. All right, final case. Case 3. Suppose that the sum k1 plus k2 is greater than n. Then the sum k1 plus k2 minus n is greater than 0. The product, which is zeta to the power of k1 plus k2, can be written as zeta to the power of n times zeta to the power of k1 plus k2 minus n, which as zeta to the power of n is 1, we simply have zeta to the power of k1 plus k2 minus n. Now, the sum, k1 plus k2, can be at most twice the largest possible value, which is twice n minus 1, which is 2n minus 2. And so, the sum k1 plus k2 minus n is less than or equal to n minus 2. That is k1 plus k2 minus n is greater than 0 and less than or equal to n minus 2. And so zeta to the power of k1 plus k2, which is equal to zeta to the power of k1 plus k2 minus n, is an element in the set u sub n. So in any case, the product of two elements in the set of nth roots of unity is once again in that set. A second important thing to notice is that the multiplication of the elements in the set of nth roots of unity corresponds to addition modulo n in the set of integers modulo n.